This is part one of two notes on section 5.2 dealing with energy, specifically our good equation for enthalpy, Q is equal to mc delta T. So let's think back to what we did yesterday. Heat and temperature, we said, are two different things that people often get confused. We said that temperature was an average of the kinetic energy, the amount of movement, and so since it is an average, the amount of the material that we have does not matter. Doesn't matter how much of the material we have, not the mass, not the volume, not the number of moles. That does not matter for temperature. Heat, on the other hand, measures the total amount of energy, so the amount of material that we use does matter. The larger the amount of a substance we have, so either volume or mass, the more heat is required to raise the temperature. And you can think about your mac and cheese that you want to make tonight that you need to boil some water for. You're going to be able to boil that water faster, change the heat of it faster, if you use a smaller pot, a smaller amount of water than your biggest pot that you have with a whole bunch of water in it, which means you get to eat your mac and cheese a little bit sooner. When the temperature of a substance is increased, the heat energy must be absorbed from the surroundings. Maybe this is from a Bunsen burner or a hot plate, or maybe just from the environment. So if I take an ice cube and put it out on my lab bench, that is going to absorb the energy from the surroundings and melt. The heat energy depends upon the temperature change, the element's properties, and the amount of the substance that we have. And we can use all of those values to calculate the heat energy with a nifty equation that we'll learn in the next slide. So first of all, how do we use these symbols and units before we put them into an equation? So the energy or the heat required is has a symbol of Q. So our symbols, we have Q, or sometimes you'll see it as delta H. The units that we use for this are joules or kilojoules, which, if you remember yesterday, 1 kilojoule is equal to 1,000 joules. The specific heat capacity, the symbol for that is C, or in some books they use S, and the symbol for it is joules, grams to the -1, Kelvin to the -1, or sometimes it's degrees Celsius to the -1. What that means is that my joules is on my numerator, and on my denominator I have grams and kelvins. Or again, it could be joules over grams degrees Celsius. Mass, we use a symbol for M, and the unit that we use is going to be in grams. The change in temperature, delta T, we know delta is always change. Temperature, we've always used T. That means T final minus T initial. And we use a unit of degrees Celsius in most instances. The big equation that you're going to want to memorize is Q is equal to mc delta T. So the heat energy required for the reaction is equal to the mass of the substance times the specific heat capacity of that substance times the change in temperature that substance undergoes. Let's try our first problem. So we know that we're going to be dealing with one of these equations, so I'm going to start out just by writing the equation. Q is equal to mc delta T. And now we can read through and figure out what parts of this we have. So it says, suppose you wanted to heat 15 grams of water. So grams, we said, was going to be measuring mass. So there's my mass value. From room temperature, which is normally approximately 25 degrees Celsius. So when it says from that temperature, that means it's my initial temperature, Ti, to my final temperature, Tf, of 100 degrees Celsius. How much energy would you require? So we're looking for Q. C is given to us. The C of water is always 4.184 joules over grams degrees Celsius. So I have Q is equal to mc, and it didn't tell me the temperature change, but it told me the temperature final and the temperature initial. So I'm going to have to plug both of those in. So Q is equal to 15 grams times 4.184 joules over grams degrees Celsius times my T final, 100 degrees Celsius, minus my T initial, 25 degrees Celsius. I'm going to do what's in my parentheses first. So Q is equal to 15 grams times 4.184 joules over grams degrees Celsius times the value that I get when I subtract 25 from 100, which is just 75 degrees Celsius. Multiply that all through, and I get 4707 joules. However, this is not the correct number of sig figs. There are 1, 2, 3, 4 sig figs there, but I'm doing multiplication throughout this, and the lowest number of sig figs I have in both of those two are 2. So I need 2 sig figs in my final answer. So I would write 4700 joules. If I didn't like the way that that looked, I could make it clearer by saying 4.7 times 10 to the 3 joules. Or if it asked for the answer in kilojoules, it would just be 4.7 kilojoules. All three of those are the same value. Okay, our next problem, again, we're going to want to know that Q is equal to mc delta T. And let's look what we have. We have 10,500 joules of heat. That means our Q value is given to us, is applied to 10 grams of water, that's my M, with a specific heat capacity, C, of 4.184 joules over grams degrees Celsius. And I'm looking for temperature change, so I'm looking for delta T. I'm going to need to rearrange this equation to get delta T on its own. Since I'm doing multiplication, the opposite of that is division, so I'm going to divide both sides by MC. Cancels out on this side. So let's rewrite this so it looks a little nicer. Delta T is equal to Q over MC. Now I can fill in my values. Delta T is equal to 10,500 joules divided by my mass, 10.0 grams, multiplied by my 4.184 joules over grams degrees Celsius specific heat capacity. Once I calculate that all through and see that my lowest number of sig figs is 3, I get B for my answer, 2.51 times 10 to the 2. Our last problem is a little bit trickier. We'll still write out here, though, that Q is equal to mc delta T. The more we write it, the easier it'll be to remember it. So it says that we have a sample M of 243 grams of a metal. So we're going to write down here MM, so the mass of the metal, subscripted little m, with a specific heat capacity. So the specific heat capacity, lowercase m, for my metal is 0.75 joules over grams degrees Celsius, is heated to my temperature that's known, or given. We'll do a TG. My temperature given, 98 degrees Celsius. I take that metal that's been heated and I place it in 45 grams of water. So my new mass is of water, and the temperature that's given of water is there. And I remember from before that my C of water is 4.184 joules over grams degrees Celsius. What I want to know is the temperature of the water and the metal together. So if I take two things, put them together, eventually their temperature and energies are going to even out. So I know that my Q of my metal at the end is going to equal the Q of my water. And I can use this knowledge to say that I know all of this and I don't know Q, so I can place that in for both of those. So my mass of my metal times my specific heat capacity of my metal times my delta T of my metal is going to equal to my mass of my water times my specific heat of water times delta T of water. Now I know almost everything except the temperature that they even out to. Well, I can't have, when I have my delta T, quite equal to final and initial like I did before. I'm going to have to say that they're in different spots in my equation to get my equation to work out correctly. So let's start plugging in what I do know. I know 243 grams of sample is multiplied by the specific heat of that metal, which is 0.75 joules over grams degrees Celsius. It's going to be multiplied by my 98.00 degrees Celsius minus that temperature that I'm going to end up with. And that whole thing is equal to my mass of my water, which is 45.0 grams, times my specific heat of water, 4.184 joules over grams degrees Celsius, multiplied by, this time I want my T in the different spot, so I'm going to start with it, T minus 24.00 degrees Celsius. Now I'm going to need to distribute through, so I will multiply these two numbers together, and once I do that, I'm going to multiply it through, distribute through my parentheses. I'm going to do that on this side as well. So I get, and I'm going to write out the whole number. I don't want to deal with sig figs until the end because I don't want any round off errors. 17860.5 minus 182.25 T's is equal to 188.28 T's minus 4,518.72. Well, I want to get everything on the same side, so I want all my stuff that contains T on one side and all of my stuff that contains just numbers on the other. And I'd rather be working in positive numbers than negative numbers. So what I'm going to do is add to both sides 182.25 T's. That cancels the 182.25 T out on my left side, and I'm going to get a value of 370.53 T's on my right side. And I am going to add to both sides 4,518.72. And I get, for that, a value of 22,379.22. Now I've got to undo my multiplication that I have here, so I'm going to divide both sides by 370.53. .53 cancels out on that side, and I get a temperature value with 2 sig figs equal to 60 degrees Celsius.